Hi, I'm Inga Puma. I'm here presenting on behalf of Brian Tolk, who runs our disturbance mapping for LANDFIRE. So quickly, just to review what LANDFIRE is, a lot of you have had some familiarity with it. It's a national mapping program. It's funded by the U.S. Forest Service and the Department of Interior, Office of Wildland Fire. Our cooperators are the Nature Conservancy, and the USGS runs the actual mapping. It covers all lands, continental US, Alaska, Hawaii, Puerto Rico, and other insular areas. It was spurred by the National Fire Plan and the Cohesive Strategy and chartered by WFLIC in 2004. And we map vegetation type, cover, and height for every 30-meter pixel across the United States, as well as surface fuel models and canopy fuels. And so those are applicable to all kinds of things, species monitoring, land cover, disturbance, fuel treatments, and fire behavior modeling. You can see down here on the bottom, we have many versions. The first one was circa 2001, sort of a base map. Then we've had many updates in between, but I'm going to be focusing on our most recent kind of complete remapping, which was circa 2016. So we have a lot of spatial layers, 32 spatial layers, all but 2 are 30-meter-kilometer resolution rasters, and the base imagery that we use is Landsat to create these layers. I'm going to focus on the disturbance, but here the reference data set includes our point data for plots as well as our events perimeters, which I'll talk about a little bit more. But the reason that disturbance is so important is because it's kind of the beginning, right, in terms of adjusting vegetation type, cover, and height for those disturbed areas, as well as the fuels that need to be changed for disturbed areas. So what do we have? We have annual disturbance from 1999 through 2016. You can see how Hawaii was added around 2011. We also have insular areas for some insular areas for 2015 and 16. There were some big improvements in that 2011 time period with sort of the base imagery that we used to calculate disturbance. And then in the remap, we continued some of those improvements. Our goal is to decrease the latency, increase the frequency, and include fewer years of disturbance with each release as we work towards an annual update. So how do we do it? We have a prioritization process that we bring in sources of data from all over the place. So what we use as the definitive source of disturbance for a particular pixel is based on this prioritization. So you see at the top is the fire program data. Those are national fire mapping programs. And we have a change detection in-house that we use, and I'll talk more about that. We have events, which are submitted perimeters from the federal, state, local, nonprofit folks that just send us their shapefiles of what happened in certain areas. So first, the fire program data, that's your monitoring trends and burn severity program, and they map fires 1,000 acres or more in the west part of the United States and 500 acres or more in the east. And all of these national fire mapping programs are essentially based on the DMBR, the normalized burn ratio, which exploits the spectral response curves, the difference between the healthy vegetation and the burned areas for the near infrared and the shortwave infrared. And so that also the difference between these curves basically gives you severity as well for that disturbance. So there's very little of these to the bark and the ravage are more based on federally requested information right after a fire for restoration efforts. There's very little of this data in the East, actually. So for our own change detection process that we use within LANDFIRE, obviously there's always that first step of image composite preparation. And so for remap for the continental US, we mainly use this best pixel process where you take the 6 best pixels centered around your target date and use the one that matches the best in terms of a similarity index. And so we use, we get early season, late season for pre-disturbance and post-disturbance for all of these different images. And this is for all of the bands in Landsat. And then we kind of had to switch when we moved up to Alaska because the best pixel wasn't working too well. There weren't enough clear pixels up there. So Brian Tolk developed this percentile composite process where, you know, you take the range of dates and that depends on latitude, right? For early season and late season. Alaska is obviously going to be different than Texas, for example. But you take the range of dates and all the imagery within the range of dates and you order them in terms of reflectance values, and then you take the 50th percentile. So you're essentially getting the middle value for each pixel within that date range. So once we have those nice clear images, we go ahead and do our remote sensing of late landscape change. So the RISLIC process, and we had 3 major ways to look at change. One was the XGBoost machine learning algorithm. We used the gradient boosted decision tree process, and it used 2 previous years of disturbance in order to train the model to recognize disturbance in the current year. So that was developed by Josh Bacot and within the LANDFIRE team. And then we also just sort of do our typical, just regular normalized burn ratio NDVI for early season and late season, just to have that kind of straight data for the interpreters to look at. But our real kind of workhorse is the MICA process, the multi-index integrated change analysis. And that one uses the DMBR, the NDVI, and then some change vectors to give the image interpreters an index of kind of the change within that tile. So the analyst accesses all of these different layers to determine if change occurred. The likelihood of whether change occurred grows with multiple layers of evidence. Okay, so we're using all of these different sources. And then another source that we have is our events geodatabase. And again, those are the shapefiles, the perimeters, the polygons that folks submit to us from all different sources. And you can see, like, from 99 to 2016, there's a lot going on, but you can also see that there's some patterns of reporting, right? So this state did better than the one below it. So it's not, we don't want to rely only on that. And that's why we have our change detection in-house. But this data set provides a lot of information in terms of disturbance types, right? So you know what happened there. And so for 2016, you can see, it's a lot less for 1 year, but there's still a lot of good information there. So we bring all that together in our prioritization process. And then we come up with an annual disturbance, and this is what you get in the legend. So for example, for 2016, you would open this up and these would be all the attributes that you would see. So the disturbance type, the confidence in the type, and that has to do with our prioritization, the severity, the confidence in the severity, and then up to 4 sources per class. So from all of those different sources that we use. And then there's actually a really detailed descriptions that kind of tells you exactly, like, how did we get to this particular disturbance on this particular pixel and where we got that information from. So here's an example of the 2016 disturbance layer. We always get a nice little signal of fire from the Flint Hills. But you can see sort of all this white area where we're detecting change, but we don't necessarily know exactly what it is in some of those areas. And so when you look at the last 10 years kind of mushed together in our HDIST layer, you can see really clear patterns of fire in the west, that Flint Hills area. You can see insect disturbance in the northeast, but you see in the southeast where I've zoomed in here, you can see a lot of this kind of just white speckle. And that's, typically mechanical removal on private lands, which we wouldn't pick up otherwise. And I think the RISLIC process really contributes to picking up on some of those disturbances. You also see some submitted events of tornado tracks. And I imagine we'll have, for 2018, we'll see a pretty good signal, right, from Hurricane Michael, which we were just talking about. All right, so how does that affect our mapping of vegetation? Well, you can see here, this is the Soberanis fire from 2016, south of Santa Cruz, about 132,000 acres. You can see the high, medium, and low severity within that. Then you go over to our existing vegetation cover. So this is percent.
Dr. Puma, this is your 11-minute warning.
Okay, thanks. I'm almost done. And so you can see how the severity of the fire affected the vegetation cover and post-fire. So that's one way that the disturbance changes our maps. And then for fuels, we had a timber understory surface fuel model, which has a pretty high rate of spread and flame length, and that got changed to sort of a timber litter model in this area. So you can see some of those differences in the surface fuel models, and that's important for fire behavior modeling. So what's next? We want to make some more improvements on that percentile composite process. We're testing the cloud for downloading, storage, and processing. We'd like to access some of that Sentinel data as well. We want to condense our timeline while still utilizing those stakeholder events with that crucial information about disturbance types. Streamline our legend, reduce duplication of efforts, for example, in DMBR calculation from different programs, and then target our modeling for machine learning and problem areas to decrease the amount of time that our image interpreters have to spend on those areas. So I invite you to explore our website, ask our help desk for any questions. You're always welcome to email me. And I want to acknowledge the entire disturbance team, LANDFIRE team, and Tim Hatton, who's our USGS PM. And that's it.
Okay, thank you. I think we have time for a few questions. I see a question in the Q&A for you. The question is, would you mind sharing why XGBoost was chosen, and were other ML algorithms considered?
Yeah, I would have to ask Josh why he chose that one. I know that there's generally they try lots of different ones and try to figure out the best one. So I will direct, if you would like to send me your information, I can direct you to Josh Picot and he will be able to answer that question.
Sure, thank you. I have used a few of them, and XGBoost has tended to underperform for me. So I was just curious, if you saw, there's always the high possibility that I'm doing something wrong. So I'll reach out. Thank you very much for the answer.
Yeah, I'm happy to explore that with you, definitely.
I see another question in the chat box. So the question is, can you point me to the best source of documentation for your whole process and maybe some of the relevant scientific publications?
Yeah, I would say in terms of for remap for the latest, I would look at again, Josh Picot did the remap prototype paper, so that's available. And if you go to our website, we have so much information, and there's actually a document search within the regular search page. So We have a ton of information on our website. I mean, it's just, and if you get lost in there, just again, email me on your specific question and I can point you in the right direction.
Thank you so much for that. We'll move on to the next speaker now.